So this mini tutorial is going to cover the electrical activity of the heart, and we're going to look at where in the heart this electrical activity is generated and where it passes to during the cardiac cycle. Now, the first thing that I want you to realise is that all of the muscle cells in the heart are able to contract on their own without any external stimulus. And in fact, if you think about it, this is practically a really useful thing to know, because if the heart wasn't capable of doing that, then heart transplants would not be possible. Because when you take a heart out from an organ donor, you sever any of the nerves that go into the heart, but that heart is still able to beat. So the heart muscle cells have a property called myogenicity, which means that they are able to beat at an inherent rhythm of about 40 beats per minute on their own without any external stimulus. But as you know, the heart rate is a lot higher than 40 beats per minute. So what this tells us is that there is actually a place in the heart where the intrinsic rate of the cardiac muscle cells is a lot higher. And that place is in a region which I'm going to mark in green here, called the sinoatrial node. Now, the sinoatrial node fires at a rate of approximately 70 times per minute. And this is in fact one of the major sites at which your heartbeat is regulated. Now, in order for us to appreciate the rest of the electrical activity of the heart, I think it would be useful for us to draw a little cartoon diagram of the heart alongside this three-dimensional rendition. So here's my version of the heart. This is my cartoon version of the heart. So we can see the basic shape. We can split it into its four chambers. So we've got the left ventricle, the right ventricle, the right atrium, and the left atrium. We can see on this cartoon that we have got a septum, i.e. a wall separating the right and left ventricles and the right and left atria. And in addition, you can also see that there is a septum separating the atria from the ventricles. And this is actually really quite an important structure for reasons that we'll come on to slightly later. But one of the main properties that this has got is that it is an electrical insulator. So we drew on the sinoatrial node on the three-dimensional image of the heart, so let's put that onto our cartoon version. And what you can see is that the sinoatrial node is present in the right atrium. Now, when the sinoatrial node fires, the electrical activity propagates through both of the atria, a bit like ripples on a pond when you throw a stone in. So here's the electrical activity propagating through the atria. And as that electrical activity propagates, it causes the atria to contract and push blood down into the ventricles. Now, on the diagram on the left, this has been depicted by showing certain fibre tracts emanating from the sinoatrial node. So sometimes when you do dissections of the heart, you can actually see these thickened bundles of muscle which kind of act as wires to transmit the impulse from the sinoatrial node. Now, as we said earlier, the septum between the atria and the ventricles is a very effective electrical insulator, apart from at one point. So on the cartoon I'm going to show this one point here in orange, and that point there in orange is called the atrioventricular node, so the AVN, and we'll just write in green the SAN. So the atrioventricular node is the single point in the atrioventricular septum where the tissue actually allows electricity to pass from the atria to the ventricles. And on our image on the left, the AV node is approximately here. Now, when the electrical activity from the atria arrives at the atrioventricular node, the electrical impulse is carried extremely quickly down through the interventricular septum along what are called the His-Purkinje fibres. And these are specialised cardiac muscle fibres which don't really contain contractile proteins, but which are specialised for conduction of electrical impulses. And you can actually see some of these fibres in the three-dimensional diagram on the left-hand side. And when you look, you actually see that they're kind of split up into two bundles, one that goes to the left ventricle and one that goes to the right. So on our cartoon, we can show how this electrical activity propagates down through the ventricles. So it goes down along the septum, and then it actually goes back up through the ventricular wall on each side, like this. On our 3D diagram, we can show that. So it goes down, it splits up into the right bundle, which goes to the right ventricle, and the left bundle supplying the left ventricular wall. So from this you can see that the first part of the ventricles to contract is the interventricular septum, followed by the apex, then followed by the rest of the ventricular walls. And you can also see why the presence of the electrically resistant atrioventricular septum is so important, because we don't want this impulse to go from the ventricles all the way through to the atria again, because what we risk at that point would be a kind of circus of activity where the electricity is going round and round and round, and this can lead to a very severe form of cardiac arrhythmia called a reentrant tachycardia. So the electrical insulator, which is the atrioventricular septum, is a very important structure in the heart, and it can go wrong in some people. I hope you've enjoyed this short tutorial. If you've got any feedback, then I'd greatly appreciate it. Thanks a lot. Bye.